Now, just so you guys know, when you get to university, nobody waits for you. They just start talking. They're not like, oh, we're on this page, or, oh, take your paper out. They just start talking, and you need to be ready to go. So have your computer out, have your paper out, have your pen out, just go. All right. Not all weak bases are amines, okay? Other common substances that act as weak bases are some of the anions. And you're familiar with those already because you've seen them on your data booklet, yes? Now, these are the anions that definitely do not act as weak bases. ClO4 minus, I minus, Br minus, Cl minus, NO3 minus, and HSO4 minus. What do all of these have in common? The negative sign. Well, yes, but so will all the other ions that we look at, anions that we look at that are weak bases. These are the ones that are not weak bases. You don't recognize anything about them that looks familiar? They're all the conjugate of strong acids. Okay, so if we go on our chart, we can see we have all of these guys are over here, and they are all too weak to act as bases. So these anions are all the conjugate bases of strong acids. Remember, the stronger the acid, the weaker its conjugate base. Therefore, conjugate bases of strong acids are so weak that they are unable to accept protons and act as bases. So, other than the two strong bases, who are the two strong bases? NH what? NH2 minus and O2 minus. Those are in the gray section at the bottom of the table. And the conjugate bases of the strong acids, these are strong bases. These guys are not bases. All the rest of the anions on the table are weak bases. In other words, those in the white section of the data table. So if you look on the right-hand side, it starts up at IO3 minus and goes all the way down to OH minus. And we can just take I just threw that little portion up there, but you can actually take a look at your data booklet, right? And you can say it's going to be everything from here all the way down to, I guess we'll leave out NH3 because it's not an anion. Whoops. Oh, and I guess I should leave out Cr2, blah, 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 blah. Anyway, you get the idea. I'm going to stop trying to highlight them because I keep missing ones that are either positive ions or neutral. Okay, I should have left out some of them. That's okay. You get the idea, hopefully. Anyway, and if you don't, you're going to ask me about it. All right. You will not be given the Kb for these anions since there is a simple calculation to find the Kb of an anion. And that is from the Ka of its conjugate acid. So if you have an anion, whoops, wrong thing. Let's go here. If I give you the anion NO2, you will use the Ka for HNO2 to find the Kb, okay? If I give you HCO3, you will use the Ka of H2CO3 to find the Kb, okay? So let's do a few of those. So the most generic way of writing this is Kw is equal to Ka times Kb, okay? I would recommend writing it as Kb equals Kw over Ka of the conjugate, whoops, acid, or Kb equals Kw over Ka of the conjugate acid. The reason I'm getting so worked up about that conjugate acid is that one of the biggest mistakes people will do is if they have an amphiprotic ion, they will not use the Ka of the amphiprotic ion, they will not use the conjugate acid, they'll use the Ka of that ion itself. And don't worry, if you're like, what on earth did you mean by that? We'll come to some examples and it will make sense. Okay, it's really hard to visualize that, okay? So of the conjugate acid. So where did this formula come from? We're only going to spend half a second on this because you do not need to be able to derive it, but this is where it came from. Let's say we have an acid, HA. Here is its Ka expression, HA over H times A over HA. The conjugate base, remember the base reacts with who? Who does a base react with? Water. And you get HA plus OH minus, and the Kb is HA over times OH minus over A minus. Now, what happens if we multiply our Ka and our Kb together? Well, we have HA times A minus. And in our Kb, we have A minus on the bottom. In our Ka, we have HA on the bottom and HA on the top of the Kb. So guess what those do? They cancel out, which leaves us with Ka times Kb is equal to hydrogen times hydroxide. And what is hydrogen times hydroxide? Hydrogen times hydroxide is Kw. So Ka times Kb is equal to Kw for a conjugate acid-base pair. Like I said, you do not need to be able to derive that. You just need to be able to know it. Okay? This works not only for anions, but also for molecular uncharged bases, like ammonia. So for ammonia, the Kb of ammonia is equal to Kw over Ka of the conjugate acid. Who is the conjugate acid? NH4 plus. So let's calculate that. What is Kw? 1.0 times 10 to the negative 14. And then you would have to look up Ka of NH4. Oh, there's NH4. 5.6 times 10 to the negative 10. And that is 1.79, which would become 1.8 times, times 10 to the negative 5, times 10 to the negative 5. Is good? Okay, easy enough. KW divided by KA will give you KB. Now, let's calculate the KB value for F minus. Do you guys think you could do this one by yourselves? Do it. Okay, so just remember that although when we had amines, we put the H on the end of the N. When we have an anion, we're going to write the acid just normal, like HF, okay, not FH. And we will end up with OH minus. And then we say to ourselves, is this actually a possible reaction? Under what situation would it not be a possible reaction? Say I had Cl minus, and I said, could this happen? Is that possible? No, because this is strong, so this does not happen. Okay, so always check to make sure that you have produced a weak acid, because if you produce a strong acid, the reaction simply will not happen. Okay, so we are finding Kb of F minus, which is equal to Kw over Ka of the conjugate acid. And one way to do that is just to write the conjugate acid down there. That's your conjugate acid. So you don't have to write out the whole word conjugate acid. You can just actually write the species there. Stick an extra H on the F. And that is equal to 1 times 10 to the negative 14 over, and you have to look up HF up here somewhere, 3.5 times 10 to the negative 4. .85 times 10 to the negative 11, and so we would round that to 2.9 times 10 to the negative 11. Now, if you were going to do calculations with this, you would not round it off. You would keep it to a couple extra digits, okay? Especially because that's like halfway in the middle, and that's the kind of number where rounding is going to it's going to bite you if you actually round off, if you've got further calculations to do. Okay. It might be a pain in the butt to always be writing out Ka of the conjugate acid, but it prevents this mistake. Now, this is the mistake I was telling you about. Find the Kb of HCO3, and here is how to do it wrong. Kb of HCO3 is equal to Kw over Ka. Notice I haven't written of the conjugate acid. And I look and I say, oh, look, here is HCO3. Yes, this is on my data table. And I look up its Ka value, and I get 5.6 times 10 to the negative 11. And that's equal, when I do the division, I get 1.8 times 10 to the minus 4. What did I just do wrong? This number is the Ka of HCO3 minus. We should use the Ka of H2CO3, the conjugate acid. Oh, look, I put space for what have I done wrong. Anyway, it's okay. So if you do it correctly, you would have Kb equals Kw of HCO3, Kw over Ka of H2CO3, which is equal to 1.0 times 10 to the negative 14 divided by, and now we find our H2CO3, that's 4.3 times 10 to the negative 7, and we get 2.3 times 10 to the negative 8. That is like a weird 3. Let's make that look like a 3. 3, there we go. Is good. So the only time to watch out for it is when you have an amphiprotic anion. You might be tempted to use the Ka of that ion rather than of its conjugate acid. Are we good? Good. All right, please do example 3. And what do you discover? No reaction. And why is there no reaction? HBr is strong. Okay, so just watch out for the strong ones. There's some exercises. We're not going to do them. You can do those over the weekend. And we're going to start hydrolysis. This is on page 34. Hydrolysis is actually nothing new, okay? It just involves taking the salt and dissociating it, and then seeing if each of the ions can react with water. But people get confused because they forget to take the salt apart first, okay? That's where people run into most of their difficulties. But you should be familiar with what hydrolysis means. It is literally the reaction of an ion with water. What have we just been doing? We've been doing some anions with water, yes? And when you react this ion with water, you get an acidic or a basic solution. Some ions can undergo hydrolysis. Can you think of some ions that cannot undergo hydrolysis? Tell your partner. How many people think they know? One person, two people. You're gonna kick yourself because we've just looked at them. Literally, like 5 minutes ago. The conjugate bases of strong acids. Some ions that cannot hydrolyze, the conjugate bases of strong acids. And I'd like you to write them out here. Why not? Okay, take a moment, look on your chart, and write them out for yourself. It'll help them stick in your head. Are there 6? Did I get them all? Okay, now that being said, I'm actually going to cross this one out because it can't act as a base, but it can act as an acid, okay? We'll talk more about HSO4 later, okay? So if you're not quite understanding what's going on with that, that's okay. There's other ones as well, but these are some of them, and those are the ones that we've already looked at, okay? So anytime you are looking at hydrolysis, you must do 2 steps. Step number 1 is the dissociation of the compound, okay? Which is very close to the C, just with a one-way arrow instead of a two-way arrow. And secondly, you're going to write your possible hydrolysis of the ions and see if it actually is possible or if you're going to get no reaction. So let's look at a salt, NaCl, okay? And we're going to ask ourselves, does hydrolysis occur? What's the first thing we have to do if we're being asked about hydrolysis? We have to dissociate the salt. So we have NaCl. What does it dissociate into? Na plus and Cl minus. And this is a soluble salt, so you'll notice this is a one-way arrow because this is a soluble salt. And I think for this section, I think almost all of the salts are going to be completely soluble. It's not really fun to ask you about slightly soluble salts or whatever. So now we ask ourselves, do they hydrolyze? What does it mean to hydrolyze? Give the definition to your partner, please. To hydrolyze means to what? To react with what? Water. Hydro, yes? Water to produce what? Acidic or basic solution, which basically means you're producing H3O plus or you're producing OH minus. Yes? So if you're producing an acidic solution, you're producing H3O plus. If you're producing a basic solution, you're producing OH minus. So you just take each of your ions individually and you say, does it react with water? So what you do is you say, I'm going to put Na plus with water. Okay, so I'm taking my Na plus and I'm trying to react it with water. And I'm saying, what happens here? Does Na plus accept a proton? Does it donate a proton? Or does it do neither? It does neither. Now let's just take a look at what would have to happen if Na plus accepted a proton. We would end up with NaH2 plus H2O. What the heck? Or you can put another letter there if you prefer. Okay? That's just like, does not exist. Therefore, it does not accept a proton. It's not acting as a base. Can it donate a proton? Na plus. No, it doesn't have an H. So it cannot donate a proton. It cannot accept a proton. It cannot donate a proton. Therefore, Na plus does not hydrolyze. And if it does not hydrolyze, that would produce a neutral solution. Now, to be fair, no metal ions hydrolyze. None of them, except there are 3, which we will learn more about later. There's iron, aluminum, and chromium, all 3+. And you will learn that I refer to those 3 as the creepy. Feel creepy. That helps you remember the Fe, Al, and Cr. I don't know. If you can think of another one that makes you remember it better, you can do that. But basically, if you have a metal ion, no hydrolysis, unless it's one of those 3, which we will talk more about later and how they work. Okay, so we had NaCl, we've done Na, and we discovered there was no hydrolysis. Are we done yet? No, we're not, because we need to look at the other ion as well. We also need to look at the Cl-. So you put the Cl- with water. And you say, what happens? Will it accept a proton? Will it donate a proton? Or will it do neither? Can Cl- donate a proton? No, it has no H+. Can it accept a proton? Let's take a look. HCl plus OH-. It looks like chloride could accept a proton, but wait, there's a problem. Hydrochloric acid is a strong acid. Oh dear. Okay, if you look on your chart, you can see we have this and the one-way arrow that goes towards the H+ and the Cl-. Cl- will not accept a proton. So we have to say no. No. So the answer is no, it cannot donate a proton. And if it's not donating a proton, it's not acidic. If it's not accepting a proton, it's not basic. And therefore, if this salt produces a neutral solution. Okay, neither Na nor Cl hydrolyze. Whoa, this sentence is ugly. What have I done here? I need to fix this. Since neither, let's get rid of that. Fix. Obviously, I started with one thing in mind and carried on with the sentence in a different way. The salt will produce neither H3O+ nor OH-, which means the solution will be neutral. So to find the pH of any salt, we need to look at both ions, the cation, or sorry, both anions, the cation and the anion. Now, we're going to specifically look at cations because there's not much to them. Because do you remember what I said about metal ions? Metal ions do not hydrolyze. Except feel creepy. Okay, iron, aluminum, chromium. So most of the time you can just look at it and go, oh, I've got a metal, no hydrolysis, done. Okay. However, if you do have Fe, Al, or Cr, you can get hydrolysis. And the other one that hydrolyzes is ammonium. Okay, because ammonium is a what? Look on your data sheet and find ammonium. Here's ammonium. And what is it if it is in that section of the table? It's a weak acid. So can it react with water? Yes. Okay. So ammonium is a weak acid. Now, feel creepy plus ammonium are the positive ions that will hydrolyze. Now, how are you going to remember these three and how they react? Because they do something really weird. They grab onto waters, 6 of them, okay? You might be like, wow, that's really complicated. I don't know if I will remember that. But it's okay because you don't have to. Because on your acid chart, look what it gives you. It shows you Fe hanging on to 6 waters with a 3+ charge. Okay, it shows you chromium hanging on to 6 waters with a 3+ charge, and aluminum hanging on to 6 waters with a 3+ charge. And if you look over on the left, the reason you can find them easily is because the names are very long. Long name. Long name. Long name. Okay, so if you're like, whoa, these are all short little names, right? Whoa, look, these ones are very long. And what are those names? Because this iron has 6 waters attached to it, it is called the hexa, meaning 6, aquo, meaning water, iron, ion. The hexa, aquo, iron, ion. Whew, it's a mouthful. And then we have chromium, 6 waters, hexa, aquo, chromium, ion. And aluminum, 6 waters, hexa, aquo, aluminum, ion. Do you need to memorize those? No, because they are on your table. Okay? And if you're like, well, how do I know how they react? Well, guess what? It shows you that too. It shows when it gives off a hydrogen, it becomes Al, instead of H2O6, it becomes H2O5. One of those waters loses a proton and becomes OH. Okay, so again, you don't have to remember it. It's right here for you. Now let's look at this in a little bit more detail. When we have iron, for example, and it goes into water, it starts out without any waters attached. And then the waters, 6 waters, attach. So you end up with Fe bracket H2O bracket 6, and water has a charge of 0, iron has a charge of 3+, so the charge is still 3+. This is the way that we write, this is called a complex ion. Okay, and in university, these things freaked me the hell out. I was like, what is this? Because they'd give us like other ones and expect us to name them, and I had no idea how to do it, right? It's okay. All right, now here's how they actually do it, right? We've got this iron, it's got a 3+ charge on it. the lone pairs on the water, on the oxygens, are attracted to that positive cation, okay? It also has something to do with empty D subshells, which you have never heard of. Anyone heard of an empty D subshell? No. Wait for first year university. That'll be exciting for you. I didn't understand those either. D subshell, what? Okay, so those lone pairs, for the purposes of Chem 12, you can just think of them as being attracted to these ions. Why these ions in particular? We will leave that for your university professor to talk about. Okay? Do you need to be able to draw this thing? No, you don't. But it's just to give you an idea of what it is. It's this ion surrounded by a shell of waters. Okay? And what can happen is we're like, oh, I have this guy here. Can it act as a base? No, it cannot accept a hydrogen, but can it donate a proton? Well, now that it's got this water, there's lots of hydrogens to be donated right here. Yep. So one of those waters so instead of having 6 waters, now we only have how many waters left? 5. H2O5. And if water donates a proton, what does it become? If H2O donates a proton, it becomes OH minus. Yes? So that means we're going to have an OH. And because it's negative, instead of being 3 positive, this is now going to be 2 positive. Yeah? And where did that hydrogen go, that donated proton? The hydrogen was transferred to the water. And what does water become when it gains a proton? H3O plus. Okay, so hydrolysis is always going to produce either hydronium or hydroxide. In this case, it is producing hydronium. And if you see this, you can say, oh, look, this produced hydronium. Therefore, this is an acidic solution. That should be a C on the end. Acidis. Sounds exciting. Acidic solution. So when Fe3 plus hydrolyzes, it produces H3O plus hydronium, meaning the solution will be acidic. You do not need to memorize this reaction because it is in your data table. The other 2 ions, the Al and the Cr, the metal ions, react in exactly the same way, so I'm not going to write them out. The only other one is ammonium. Could you please write the hydrolysis reaction for ammonium? We have NH4 plus H2O. NH4 is a weak acid. You'll find it on the weak acid side of the table. So it is the proton donor. That makes water the proton acceptor, the base. If NH4 donates a proton, what does it become? NH3. And what does water become? H3O plus. So, just like the hexaaquo ions, ammonium produces H3O plus when it hydrolyzes, and therefore the solution will be acidic. And because there's only 4 of them, they all produce H3O plus, they all produce acidic solutions. Cationic hydrolysis is always acidic. I'm going to try and draw a lemon because it's acidic. But, huh? Color the cat red? Okay. So it's acidic? Okay. Highlighter. Oh, I don't have a red highlighter. No, I don't. I have a red pen. See? Oh, that was sad. Okay. Whoa. Okay, and a lemon looks kind of like this. So just imagine a cat with a lemon. Cations always produce acidic solution. I don't know, maybe just having watched me do that horrible art presentation will have helped you remember it. I don't know. Cationic hydrolysis is always going to produce an acidic solution. Please write the hydrolysis reaction that occurs in a solution containing chromium. Do it. And hopefully you didn't spend too long thinking about that, but just looked on your table, right? Unless you happen to be able to just remember that, in which case you are incredibly lucky to have such a good brain that is so kind to you. Does that mean then that if I have an anion, that anions will always produce a basic solution? Well, no. Anions are more complicated. Anionic solution hydrolysis usually produces a basic solution. However, some of your anions are amphiprotic. Yes? So amphiprotic anions can produce acidic or basic solutions. In fact, they produce both. They actually produce both. H3O plus and OH minus. And it just depends on which one they do more. pH depends on which reaction happens more. Okay, most anions just produce the basic solution. But the amphiprotic ones, we have to be a little more careful in our look here. So let's take a look, first of all, at a solution of KF. So first of all, you need to recognize that KF, what kind of a substance is it? Is it an acid? Is it a base? Or is it a salt? It is a salt. Okay? Acids, H something, or something COOH. Yes. Base, something OH, or an amine. And what does it mean to be a salt? What's another word that means exactly the same thing as salt? A salt is an ionic compound. And the only little difference is it's an ionic compound that does not contain hydroxide. Because if it contained hydroxide, it would be a base. I knew you knew that. I knew what you meant. So basically all ionic compounds are salts, except if it contains OH. All salts are ionic compounds. They mean the same thing. So do we have an acid, a base, or a salt? You look at this and you're like, oh, I got a metal and a nonmetal. That's an ionic compound. There's no OH, therefore it is a salt. And if you're asked for the pH of a salt, you're going to, 1, dissociate, and 2, you're going to hydrolyze the ions. And that means react the ions with water. I need to come up with a little device for this. There's no weak little old lady for this one. So if you guys think of something really clever to remember, if you're asked for the pH of a salt, you have to dissociate it and then hydrolyze the ions. This one sounds like it's going to be hard to come up with a mnemonic device. You might just have to remember this on your own without pictures or anything. Okay, so we have KF, and the first thing we have to do is dissociate it. What does KF turn into? K plus and F minus. And then we have to ask ourselves, does the K plus hydrolyze? And remember, this is a metal, and it's not feel creepy. Therefore, does it hydrolyze? No. Okay, so you need to memorize that. Metals do not hydrolyze unless it's feel creepy. Does F minus hydrolyze? Let's try it out. If we take a hydrogen from the water and put it onto F, what do we get? HF. Plus, who's left over? OH minus. Is HF strong or weak? It is weak. And if this is weak, then we say, yes, hydrolysis. Okay, yes. So the above equilibrium can be set up. So hydrolysis does occur. And then you say to yourself, did we produce hydronium or did we produce hydroxide? What did we produce? We produced hydroxide. OH minus is produced, therefore the solution is basic. So assuming that a cation does not hydrolyze, which is often the case, if the conjugate acid is weak, anionic hydrolysis does occur and the solution will be basic. If the conjugate acid is strong, the anionic hydrolysis does not occur and the solution will be neutral. And this is, but check if amphiprotic. Okay. Do you think you guys could tell if NaCN is acidic, basic, or neutral? Try that next one. Try example 5. Is good? Okay. CaBr2. Try it. If you're done, you can check your answer up here. This solution should be neutral. And when you get good at doing this, if this was a multiple choice question, you wouldn't go through all this work. You'd be like, calcium does not hydrolyze, it's not feel creepy, it's not ammonium. Bromide, oh, I know that's the conjugate base of a strong acid, so no, it's neutral. And you just be like, this salt is neutral, okay? Now, how about SrNO2? Is it acidic, basic, or neutral? Could you try that one, please? So I've kind of written up two ways of thinking about this. The one on the right-hand side is more what we've been doing. We dissociate it into the two ions, Sr2 plus and 2NO2 minus. You try to react each ion with water. Does Sr react? No, most cations don't. It's not feel creepy or ammonium. Does NO2 react? Well, you stick the H on the NO2 and you get an acid and you say, oh, that's a weak acid, so yes, it hydrolyzes. And because we made OH minus, it is basic. The method on the left is sort of more what you might do for a multiple choice in your head. You might say my ions are Sr2 plus and NO2 minus. Sr2 plus does not hydrolyze. I know there's only 4 cations that hydrolyze. NO2 minus, I know its conjugate acid is weak, so yes, it does. Anionic hydrolysis is basic unless you have an amphiprotic anion, therefore the solution is basic. So that would be sort of like more like a multiple choice strategy. Yeah? Usually if you're given it in a written response, you'll be expected to write the hydrolysis equation. Okay, so, but this is a The one on the left is kind of good for solving in your head real quick. Okay? Common error alert. Many students think that I've formed a weak acid, so therefore the solution is acidic. Okay? Except that every side of an acid-base equilibrium has both an acid and a base. The acidity or basicity depends on whether you have OH or H3O+. So don't worry about, did I form an acid, did I form a base? No. Look for OH or H3O+ to decide. Okay? And we don't have time to go through amphiprotic ions today. Can I post a video on amphiprotic ions that you watch over the weekend? And then you can do the problems in this section. Okay, so your homework will be to watch the video and then do, you know what, I'll post the homework online. Is that okay? Yeah. Because we're almost out of time. And yeah, there we go. All right. So there will be a video, there will be some calculating KB from KA, and there will be some hydrolysis questions. Hi. Oh, okay. You have a pen. Oh, exciting. There you go. Thank you. And have a happy weekend. Ooh, we have to have a quiz next week though. And it has to be on KB and indicators. Wednesday? Okay, and then the day is the day after the grad ceremony. So we get to have it on Wednesday or Thursday. Are we having it on the day of the grad ceremony or the day after the grad ceremony? Day of? Okay, and if, what? I said like half our class is like grade 11. Yeah, plus, what are you doing during the day that you can't, like, write the quiz? Not going to school. Oh, why? I will go to school. Okay. Now I have to. Now you have to, yes. Okay, so yeah, there will be a quiz next week on on indicators and KB, not hydrolysis, Wednesday. Not hydrolysis. 3.1 and 3.2, or 5.1 and 5.2. That's fine. We just need 3 so. Have a lovely weekend. Yeah. Did I leave you in the prep room? Because I love this unit. I hated solubility. I didn't understand anything. I don't know that. Equilibrium and solubility. Maybe because it's really new concept. Find expense, Yes. It's either Wednesday or Thursday.
Can we have it Thursday? Thursday.
Why?
Wednesdays are grad.
Yes. And Thursday's the day after grad. What are you going to be doing with yourself on Wednesday? What for? When is it?
We have to be there at 5. We have to find out where it is, so probably 4:30.
I'll tell you what. If you don't want to write it on Wednesday, you can come during flex on Thursday. Okay? Yeah.
Or I can do it Tuesday.
Or you can do it Tuesday. That's fine too. Yeah. Either way.
But on flex.
Yeah. Yeah. It'll be a bit long though, so maybe I'll like split it in half. She could do like half one day and half another day. Hi?
The maps.
Pardon me?
Like the maps.
Yeah.
When
Oh, well, I'm marking them this weekend. You're like, oh dang, that's not gonna work for me. Just give it to me on Monday, okay?
Oh no, it's not Monday.
Or Tuesday. Tuesday. Yeah?
I don't know where to start from.
Why don't you come in Monday morning and we'll go over it together? Tuesday morning. Whatever day we start back at school next week, why don't you come in that morning and see me about it? Does that sound good? Okay. Don't worry, we'll be fine. I'll help you out, okay?
How are you?
I'm all right. I'm excited for the weekend. No, I will not. But I'm legit this time. Like legit. I've got Am I still recording? Oh, I am. How wonderful.
Just put it out there.